Mpirical provide compelling, interactive learning across a range of delivery options. Live on site, live online, or online anytime, we have a training course that is ideal for you. For a no-obligations chat about your training requirements, contact us at mpirical.com.
The composition and the consistent annotation of an IPv6 address is an important factor to consider when looking at IPv6 as an overall concept. So in this session, we're going to first of all look at the composition of our IPv6 address, and that will include exactly how we correctly annotate that address in accordance with the rules laid down by the Internet Engineering Task Force. If we look at the overall IP addressing associated with v6, we know that that address is 128 bits in length. Now that is not very human friendly to deal with. So as a start, that 128-bit address block is actually broken down into smaller blocks, 16 bits in length. So as a consequence, we have 8 16-bit blocks. Now, just like in IPv4, part of this address is going to denote a network ID or a prefix. And all devices on the same network, just like in IPv4, will share the same network ID. The other element of the address is the interface ID, and this is different to IPv4. In IPv4, we have the host ID. Well, in IPv6, it's been recognized that an individual device may actually have several different interfaces. It may be what is called multi-homed. So each interface could potentially have a separate IP address. So in IPv6, we have this notion of an interface ID. And just as a general rule, for a typical unicast IPv6 address, the interface ID is 64 bits long. Now this in and of itself, 64 bits, is a colossal number of bits just to identify the interface. However, if we delve further into this address composition, particularly with respect to the network ID, in actual fact, we can break this network ID down even further. And again, this is similar to IPv4, because in IPv6, it's recognized that subnetting of the network will be required because we are dealing with such very large address spaces. So in reality, we can break this prefix, this network ID, down into what is called the global routing prefix. So this is the element of the address that ultimately gets us from our source network to our target network. But once we get to the target network, we can then subnet the network down so that the network address space is more manageable by the routers on that target network. And as a general rule, again, for unicast addressing, we see global routing prefixes of 48 bits and our subnet ID is 16 bits in length. Now that equates to over 65,000 different subnets on one network, so it's still a considerable figure. Now this is a rough indication, these are typical figures, but you may see these figures sliding slightly to either increase or decrease the subnet ID field. Now, just like in IPv4 classless interdomain routing, we also have slash annotation. So remember that slash annotation denotes the number of bits that are actually being used for the routing prefix, the global routing prefix. So if we are using 48 bits for our global routing prefix, it would be a /48 address. So by looking at that slash annotation, we can immediately identify which bits identify the network. So as you can see, in terms of annotation, we do have a large number of bits, and even if we break those bits down into 16-bit blocks, it's still a difficult address size to manage. So it's difficult for a human to work with, And as a consequence, we've already identified that we have 8 16-bit chunks comprising our 128-bit address. So the first step to take in terms of annotation is actually to turn these 16-bit chunks into hex. So let's identify an individual chunk. So what we can do is we take those bits, so the 16 bits, we can take the 4 first bits and turn them into the hexadecimal equivalent. And if you factor that in, if you work that out, the equivalent in this example, 1101, is hex D. So we will do that for the remainder of that individual block. But as you can appreciate, what we'll actually do is do that for every single block in the entire address. So we're just picking on one block here, and overall we actually need to do that for the entire address space. So there you can see each 16-bit chunk is separated by a colon. So once we've conducted the binary to hex conversion, we can separate our 16-bit chunks using a colon. And that is the typical format for our IPv6 address. It is termed colon hexadecimal. But as you can appreciate, it's still a very long address. So there are additional measures in place which make it even easier for humans to deal with. So let's consider some of those techniques that can be used. So here we have an IPv6 address, and as you can see in this IPv6 address, the first thing I want to point out is there are strings of consecutive zeros, or consecutive zeros within one 16-bit block. So after our first 16-bit block of 2003, we see 2 separate 16-bit blocks with consecutive zeros. And what we can actually do is contract them down. Watch what happens in the animation here. So we lose our 16-bit blocks of zeros and we actually replace them with a double colon. Now the point to note about this is we can only do this once in an address. So notice in our preliminary address we actually have an additional set of consecutive zeros. We are not allowed though to use this double colon technique twice. So we would use the technique on the longest consecutive set of zeros. So that's one mechanism that we can actually use, and quite clearly you can backwards calculate how many 16-bit blocks we're actually contracting down there. Another technique we can actually use though is to drop leading zeros. So if you look at our address at this present time, a number of our 16-bit blocks start with a 0. So for instance, the second 16-bit block we can see 0E5C. Well, what we can do is drop the leading 0. So our address now turns into this address, and you can see which sets of zeros have actually been dropped as a consequence of that. So there are techniques, primarily contracting any multiple sets of consecutive zeros and also dropping leading zeros, and the result of this is to ultimately make this address more easy for a human to deal with. But these are options, and the problem with this being optional is what you find out there in the IPv6 world as a whole. People use these techniques inconsistently. Now, the Internet Engineering Task Force have recognized this fact, so they have released a request for comments document which is essentially a set of guidelines for exactly how we should consistently denote or annotate our IPv6 addresses. So let's take a look at some of these rules. Now, the first rule the IETF have set down is leading zeros must be suppressed. So in this particular example, we've got a couple of instances in this address of leading zeros actually being present. So in the eyes of the IETF, this is not acceptable. What would be acceptable is to suppress those leading zeros. So that's our first rule. Our next rule is that the address should be shortened as much as possible. So here's our example. In this particular example then, we have a number of consecutive 0 16-bit blocks. Now you can see that we have used leading 0 suppression. So we have started to shorten this address, but remember that we can also use the other technique of using a double colon to shorten this address even further. So where possible, the address should be shortened. Our next rule, don't use the double colon just to shorten one 16-bit 0 field. So again, as you can see from our address here, we've got a double colon actually used, but if you work it out, we can still see the 7 blocks that make up our overall address. So all we're ultimately doing by using this double colon is just shortening one block of consecutive zeros. And the IETF have said that there's very little point in doing this. So the alternative is to simply just use, in this case, leading 0 suppression. The next rule, the longest run of consecutive 16-bit 0 fields must be shortened. So if you have an address like this one, you can see that we actually have 2 sets of 16-bit 0 fields. We've got one which features 2 blocks of 16-bit 0 fields, and we've got another element which features 3 blocks of 16-bit 0 fields. And as the rule says, we will shorten the longest run. So in this case, it's the second block that gets shortened. The final rule from the IETF is that any alphabetic characters should be in lowercase. So as our example, we've got uppercase letters here, and this is not allowed. We should really be annotating in lowercase. And if we do follow these rules, the idea that the IETF is really pushing at this time is to have consistent annotation of IPv6 addressing on a global basis. So just in summary then, we saw in this session that the IPv6 address can actually be broken down into 3 main areas, and those are the global routing prefix, the subnet ID, and the interface ID. We also saw that / annotation is still used in IPv6 to denote the length of the routing prefix. IPv6 addresses, we also saw, are actually turned into a human-friendly format using Callon hexadecimal. And there are various techniques that can be used in order to shorten that address down. And we looked at the concept of suppressing 16-bit blocks of all zeros, and we also looked at suppressing leading zeros. But remember, the IETF have indeed laid down a set of guidelines which, if we adhere to, it means that we can have consistent global IPv6 addressing annotation.
Need to know more? Why not visit our store, where you can choose from over 200 hours of video-based training. Alternatively, you can contact us to discuss any specific training requirements you may have.